Chalo, camps on everyone. Let's start off. Sure. So last thing we did was this one. Next thing. Stability of ships. So whenever you're designing a ship or any object, right? The thing is, think of like this. The center of mass will act on the center of mass of the body. Let's call it COM. Whereas the buoyant force will be acting on the displaced liquid. So this is your center of buoyancy. So if you design a ship where the center of mass is below and the center of buoyancy is above, see what happens. Now, if the ship tilts for whatever reason, the mg will act this way, the buoyancy force will act this way. If you see, the system will actually go back. This is a stable equilibrium. So every time the ship will tilt, it will go back to its initial position. Suppose the same thing if you design something like this. Where the ship is heavier on the top, that means center of mass is here. And the buoyant force is here. Now see what happens if the ship tilts a bit. The mg will act this way, and the buoyant force will act this way. So the torque will be this way. This is an unstable equilibrium, isn't it? You displace it, it will keep on going in that direction, it will never come back. So whenever you design ships, you have to make sure the weight is, uh, much below this thing. So there's a name for this actually. We don't have this in the portion.
So that's the reason they have that red marker line. So the ship goes up to only certain extent down, and then you can't fill it like for cargo ship.
Mm, not exactly. No, that red line you're saying on the ship ka side mein?
Yeah, so like
Normally there is a limit, right? So
yeah,
that is just to show like, that's like a safety thing or something. So mg will be somewhere here. The bind force will shift somewhere to the side. So this FB, the point which crosses this point, right? There's a name for this. It's called meta center. We don't have this in the portion, but just in case. So for stable ships, what should we do? For stability, the center of mass must be below the center of buoyant force. Have a look at this. Just a small topic about stability. So generally, one of the reasons, if you see, right, the bottom of the ships are made heavier. They keep the cargo, the engine room, all that thing, whatever is the heavier things, they try to keep it at the bottom so that they're making the base heavier. So if you see these oil tankers, they're pretty stable. But if you see a cruise ship, that is actually more unstable. Because the problem with the cruise ship is what? Everyone wants to have a view, and so everyone wants to stay in the higher floors. So they have to make the ship taller. And when you make the ship taller, the center must shift in the upward direction. So between oil tankers and cruise ships, oil tankers are more stable. You put them even in a tsunami, the oil tanker actually nothing happens. Clear this? So this is more of a stable and unstable equilibrium. Next thing. Can I turn the page? So till now, right, what we dealt was fluid statics. That means the liquid never flowed. The second part is fluid dynamics. So in fluid dynamics, right, we study fluids in motion. So if you have a liquid flowing here, what we are studying here is a small region. We call this thing control volume. So control volume is the region in which the liquid is studied. So while studying fluid mechanics, right, actually fluid dynamics studying, right, is one of the very difficult thing. So we try to keep it simple by using some variables, some assumptions. So flow or field variables. So these are the certain assumptions, which some variables which we see. The first thing, the quantities which we study in a fluid flow is pressure. The second quantity we study is velocity of the liquid particles. Third is density. The fourth is acceleration of the liquid particles. Now, we define something called a streamline. Now, when you keep saying particle, particle, exactly what's a particle here? That is one thing we need to clarify. When you say particle or in a fluid, what we mean here is collection of molecules. We're not studying about a single, let's say water has some mixed air or something. You're not talking about a single molecules. We are talking about an average. So what we are considering here is we are taking an average speed of the collection of molecules. Meaning, in this water, if you study each and every molecule, everyone will have a different speed. But if you take a collection, matlab, if you take a small region, let's say 1 millimeter cube, in that region, the average speed will be same for every 1 millimeter. Just like, in KTG, every molecule have a different speed. But if you take a small region, you can be sure every region will look identical. The average speed is the same. We're taking average speed of collection of molecules. So when you say particle, it is not a single molecule. So individual molecules have different speeds. What we are always talking is average. So when you say the speed at this point is v, we are not talking about one single molecule there. We're talking about the average speed of the molecules that reach there. Clear? It is like, think of like this. Let's say on a highway, if you say, on this Eastern Expressway, the average speed of the vehicles is 20 kilometers per hour or 40 kilometers per hour. It doesn't mean every vehicle is going with 40, isn't it? On an average, on that road, the average speed of the vehicles is 40 kilometers per hour. Maybe bikes are going faster, lorries are going slower. Now, like I said, it's quite difficult to study liquid flow. So we fix our study to a very limited thing. We study only streamline flow. So we define something called a streamline. So what's a streamline? A streamline is a curve which is tangent to the velocity vector. More of a technical thing. Let me tell you in a more simpler way of liquid particles at that instant. What it simply says, right, is the path of the particles. Means for the path, if you draw the tangent, that is a tangential to the velocity vector. The meaning of this sentence is simply a streamline is the path of the particles. A collection of streamlines is called a streamline flow. Streamline or steady flow. So again, what do you mean by this? I have explained this in steady state room or in thermodynamics heat transform. So if you take a streamline, at each point, let's say this point A, the velocity of the particles is VA. At point B, the velocity of the particles is VB. So velocity at a given point is constant. Velocity of the particles is changing, but when the particle comes at that particular point, the speed is constant. All particles that reach A have speed VA, and speed becomes VB when they reach B. The speed of the molecule, speed of the particles is changing, but they're constant with position. Let's say velocity. So here, velocity of the particles can change with time, but it is fixed with position. That is the meaning of a steady state. In this case, it's a steady flow. Clear with this? Vidyut, Neil. So far clear? Palaksh, Rehan. Everyone is given the last exam, right? I think some of you have not given the test. Now, people, if you're missing the test, I'm telling you, I told you this before also, don't do that. Give the test. And some of you are so smart. Exam deadline is 11 p.m. and then you message me at 10:30. Sir, tomorrow I have an exam I can't give. That is like, sheer, what you call, carelessness it is. If you really have an exam on Friday, when do you know there is an exam? When should you tell me? You should tell me on Monday. You should tell me on Tuesday. You should tell me on Wednesday, not half an hour before the exam. And there's one great God here. This God is like, he messages me and says, Sir, if I write the exam at 10:55, will I get time till 11:55? मतलब deadline is 11 o'clock ना, with doubt था. Will the 11 o'clock exam बंद हो जाएगा? Like, यार, you guys are so smart, like, you want to find loopholes and everything. So, I really didn't know whether to, scold him or to praise him for being so smart. ठीक है. Next thing. If you start the exam at 10:50, you get time till actually 11:55. But then by chance exam में कुछ हो गया and exam shuts down in the middle, you won't get a chance to write it again because the deadline got over. Now, streamlines never intersect. That means, think about it. If you have two streamlines, this point is saying the particle should go this way. This point is saying the particle should go this way. You can't have two velocities at the same point. There will be two velocity vectors at the point of intersection, which is not possible. That's why streamlines never intersect. Greater the streamlines, greater the velocity. If you have more streamlines packed up in a small region, implies the faster the liquid is flowing.
How do you define the density of a path of
Density.
you said streamline is a path of a particle.
Yeah.
So how do you define the density of streamlines?
Density or the number of streamlines per unit area. Right?
Oh, okay.
This is the number of lines by area. Meaning how crowdly they're packed. So if you look at this point here, so if you take this point B here, and if you take this point A here, I didn't draw it properly actually. So if you look at here, there's a small area, there's a big area. Number of lines are same. So this is point A and this is point B. So velocity of B is greater than velocity of A. Okay, if you have more lines in a particular region, that means this liquid is flowing much faster. Clear? So exactly what is streamline flow? How does it look like? Let me show it on the next page. So if you take streamline flow, think of like this. It is like your traffic, which is flowing on a streamline or steady flow, like your traffic flowing on a highway. On highway, if you see most people, right, do to follow the lanes. Meaning people still jump from one lane to another, but technically speaking, people always keep going in the same lane. So if you have streamlines like this is what you notice. If you take some ink and if you start pouring it on the liquid, you'll observe after some time this entire streamline becomes red. You're getting it? So the color does not spread. Meaning if everyone follows the proper lanes in a highway, for some reason, let's say one track gets blocked, only this traffic will get stuck and remaining people are going. But if you take the other flow, turbulent or non-steady flow, the flow is messed up. Think of this Andheri streets or something, or your local car roads. People are just going anywhere from anyhow. So on this kind of fluid, if a liquid is flowing here, and if you drop ink, you'll observe wearing after stream, this thing, the entire thing is colored. The whole liquid ink spreads. So here actually there's no definition of a streamline. We don't know how the particle is going to go. Simply put it on a streamline, you can tell me where the particle is going to be next. Whereas on a turbulent flow, we have no idea what the hell the particle is doing. It is just spread over everywhere. You get the difference? Now, who decides whether the flow is steady or turbulent flow? We have something called Reynolds number. So this is given for a fluid flow flowing in a pipe. Diameter, velocity, area of cross section is A. You don't need area. D is given anyway. So the Reynolds number R is given by rho V D by eta. Rho is density. D is diameter. V is velocity or the speed of flow. Eta is called quotient of viscosity. So if R is less than 2000, it's a streamline flow. It's all experimental. If R is between 3000 to 2000, we have no idea. It can be anything. For R greater than 3000, the flow becomes turbulent. So now you tell me, for a liquid to have a streamline flow, should it have high density or low density? High viscosity or low viscosity? तो ऑप्शन 4 ऐसा होगा, हाई डेंसिटी हाई विस्कोसिटी, लो डेंसिटी लो विस्कोसिटी, हाई डेंसिटी लो विस्कोसिटी, लो डेंसिटी हाई विस्कोसिटी. for a liquid to have a streamlined flow, the density and viscosity should be what? High or low? What do you guys think? Again, think properly. You want streamlined flow. Matlab Reynolds number should be less than 2000. Means R should be small. So denominator should be big and numerator should be small. Numerator mein density hai. So for streamlined flow, we need low density and high viscosity. Yeah. That was a question in the exam, huh? Theoretical question. For streamlined flow, liquid should have low density and high viscosity.
What's the height? 10-3, 10-7-3, 10-3. That's true.
He was saying, look at the, you see the white
Flash
at the
right there.
top? Yeah.
And then you'll see when it's laminar, it'll be a straight line.
So what they're doing, right? They're sending ink from the left-hand side and they're changing the flow. Now, rho Vd by eta, if I increase the speed, what will happen to Reynolds number? It will increase. So if I increase the speed of the flow, Reynolds number will increase and the flow becomes turbulent. If I decrease the flow, V will decrease, R will decrease, and the flow becomes steady state.
Of the dye that comes out.
So let me.
It's literally mixed throughout the whole flow.
The water looks.
And if you look at the very top, that looks like a complete tube with no motion at the top of that flow and the bottom as well. When it's turbulent, you'll see like a white speck or reflection kind of speckling. So right now it's
There. Can you see the streamlines? You can clearly see the streamlines. There are actually two streamlines inside. So when the flow is less, this is how the liquid will flow. It doesn't get mixed up. The ink will follow its own path. But if you increase the speed, there you can clearly see the two streamlines. And can you see the rest of the water, how clear it is? Because the ink is not getting mixed up. But now if you increase the speed, you can see how it become everything bluish. The flow has become turbulent and the ink is just spreading out everywhere. So there is no definite path for the particles to go. So the whole thing has become bluish. This is a turbulent flow. This you'll observe even when you open your water ka tap. Kabhi observe kiya? When you open the water tap, initially the water is crystal clear. Then it becomes sort of rough and hazy. Because as the water is falling down, it becomes speed increases. As speed increases, flow becomes turbulent. So you will see the starting part of the water will be clear like a crystal, and then it becomes, more blurry. Able to visualize? When you open your water tap, you must have seen that many times. Or if you must have seen this thing in your kitchen or your washroom, you can attach a nozzle kind of thing to the tap. It has a lot of small holes. When you put your hand below that, it feels more smooth and fluffy. The water becomes more streamlined flow.
Compare that.
This is one. This is Pascal's law. I didn't show you this thing, right?
Suppose we apply an external force, as shown. The pressure from the
Remember what is Pascal's law? You increase pressure at one point, it spreads everywhere. So this is what is happening. You're pushing from
External
left.
force
See how the
spreads through the
molecules
fluid.
are spreading up.
Here, we are in a zero-gravity environment. Eventually, the pressure of the fluid will be the same everywhere throughout this container.
And there, see. You're pushing from one side. Music is weird, right?
Let's also apply an equal external force on each of the other red rectangles.
That piston thing. Hydraulic jack.
There are many practical applications of this principle, such as the hydraulic lift, which allows us to raise extremely heavy objects. This works because the force from the fluid is the pressure multiplied by the surface area, and the larger rectangle has a larger surface area. This does not violate the conservation of energy, because the energy transfer is the force multiplied by distance traveled. The left rectangle feels a smaller force, but it travels a longer distance than the right rectangle.
This is what I was telling you last time. I'll send you this. You can listen to the music later on. This is interesting.
I've come across a small video clip in various compilations on
So,
YouTube showing a small explosion going off inside of a polygon-shaped sphere.
uh, so this thing, right? Ever seen this thing? You know, people make this big spears and all. How to make circular tanks? So what these people did now? They made this rectangle, hexagonal things. They welded them properly. On the top, there's a small explosive, a bomb.
Which
See how they
forced
make
it into
spears.
a round sphere.
So what happened?
The video usually only lasts a few seconds, so I didn't know what the objects were or what was happening, but I really wanted to know. So I started doing some research and found a company in
There.
China who makes stainless steel spheres for art sculptures. The company's
So remember in ray optics we saw, remember they want to make mirrors of radius r curvature. We keep saying. So when you want to make big mirrors of radius r, the best way to make is something like this. So they take, you know, this hexagonal kind of thing. So you weld them up, you fill up them with water and put a bomb on the top. And when the bomb explodes, it will push the liquid. And from Pascal's law, the pressure will distribute in all directions equally. Now you tell me, when the liquid pushes in all directions symmetrically, what kind of shape you get? A sphere. So this is the best way to make a sphere naturally. Matlab, if you try to make a sphere with your machines and everything, that will still give an error. But this Pascal's law will give you a
forced it
proper
into
sphere.
a round sphere.
So
The video usually only lasts a few seconds. It's for art.
these are all the
Allowed
shapes.
Based off my research, there seems to be 4 common ways to create a hollow metal sphere. The 4 common ways are spinning, mold pressing, water pressure hydroforming, and explosive hydroforming.
What you saw is
Spinning
explosive
like working
hydroforming.
on a lathe. They attach a flat round blank onto a machine. While the blank is spinning at high speed, they use various types of tools to start pressing down the blank into the shape of a hemisphere. And once they've got 2 of them, they can weld them together to create a sphere. This method
That's how you
uses
make
the
sphere.
skill of an artisan and a lot of labour to create the hemisphere. But larger companies will
No, you can check it out. I'll send you that. And I showed you this, right? Drum exploding.
And it's part of the Year 9 science curriculum. Is what we're going to do is we're heating up a little bit of
Now, what this teacher is doing here, he brought a drum, he poured water inside, and they're heating it up. So when you heat the water, what will happen? The whole thing will fill with water vapor. So when the whole thing is filled with water vapor, it will push the air outside. Right? So right now what is happening is all the air is coming out, the entire thing is filled with water vapor.
going to close the lid. It'll be pretty close to
And
being
now
there.
what they're going to do,
It needs less space, and it won't be able to suck air in because the lid is going to be on.
so they removed the fire and he's sealing the top. Now see, now the whole thing inside, you pushed all the air outside and filled with water vapor. Now, if you cool this down, what will happen to the water vapor? It will condense. So vapor becomes liquid. And when it becomes liquid, it will start creating a low pressure region inside because there's no air already. So now inside you have a vacuum and outside you have an atmosphere, and atmosphere is pushing it. It starts pouring water to cool it down.
Stand your ground,
So what happened to the drum? And that is what atmosphere pressure can do. We don't feel it because our blood pressure cancels out with that, but it can be pretty deadly. Let me show you one more like that. This one. This thing, but oil tanker normally trains carry oil. So they brought a tanker, they connected to a big machine, and they're removing all the air from inside. That's a steel tanker, huh? That is what atmosphere can do to you. So next time when you breathe air, have some respect for atmosphere. So that way. That submarine thing you must have listened recently. Kuch water ke under gaya and something happened. Karke. The same thing happened. There the pressure outside was 300 atmospheric pressures. And the good thing about this thing, right? The guys inside must not have even felt when they died. So it's a good death. Meaning the pressure was so high, the whole thing, and the worst part, what? Most people think they're crushed to death. They actually got burned to death and then they got crushed. When the pressure is 300 atmosphere pressure, when the volume tries to compress, you're suddenly compressing to adiabatic compression. Think about it. If the volume becomes 1/100th of a time, temperature will rise almost 100 times. But the thing is, this thing is compressing so fast, by the time your hand gets crushed, by the time the signal reaches your brain is already crushed. So there is nothing there to receive that you are injured. So it's an instant death. You must not even knowing what happened. It is done. It's a decent way to die. Okay. So that is the thing. Clear with this turbulent flow? Now everyone understood how streamlines look like. Now we will limit our study to a very special cases like streamline flow for ideal fluids. One of the reason, when you're climbing a hill and everything, if you don't get acclimatized properly, you start bleeding from your nose because your blood pressure becomes more and outside pressure is less. So first thing, we will be studying streamline flow for ideal fluids. One, there should be no viscosity, basically no friction. Because if there's a friction, you can't conserve energy and we can't solve. Second, incompressible, meaning no matter how much pressure you apply, liquids should not compress. In reality, they do compress a bit, but almost very small. So indirectly, you're saying density is constant. Third, the flow should be irrotational. Irrotational meaning you must have seen this, whenever a liquid flows, you can see small whirlpools. This kind of things we don't want. You don't want whirlpools inside. So if you have whirlpools like that, it is called rotational flow. So for irrotational flow, again, this is slightly out of the thing, but if the condition for irrotational flow is this. del cross V bar is 0. Do you guys remember what is del? Where we have seen this? कहाँ पे देखा था याद है? Conservative force का proof था. Del cross F is 0. Conservative force में we saw that thing. So del bar is nothing but, it's called a curl operator. So dou by dou x I cap plus dou by dou y j cap. We have done this in conservative force. So del cross V bar should be 0. This is the thing. I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z. This is Vx, Vy, Vz. If this condition is satisfied, we say the flow is streamline flow. It is irrotational flow. It's called curl of a vector. We don't have in the portion. When you're engineering first year, you will learn more about it. Have a look at this. Clear? Turning the page. Dhrit, Abhinav, clear so far? No. Equation of a streamline flow. Now on a streamline, this is a velocity is the tangent. This is theta, Vx, Vy. So tan theta is the vertical component Vy by Vx. This is nothing but slope. But I also know tan theta slope is nothing but dy by dx. So we can integrate from here dy by Vy is equal to integral dx by Vx. Integrate that and you'll get the things from here. Example, they'll give you velocity v is 1 by x I cap plus 1 by y j cap. And if I ask you to find the equation here, so tan theta is Vy by Vx. In this case, it will be x by y. So dy by dx is x by y. This will be y dy is equal to x dx. Integrate on both sides. This guy will be y square by 2 is equal to x square by 2 plus constant. So this thing turns out to be y square minus x square is a constant. This is a hyperbola. Did you guys learn hyperbolas? So if you have done this, so later on they'll teach you. This is actually a rectangular thing, a rectangular hyperbola this is. So if you draw the lines y is equal to x and y is equal to minus x, let the teach you in max, but let me show you how it looks. This is equal to y is equal to x. So if that constant is 0, you'll get a straight line. So as the constant is a small positive number, the streamlines will look like this. They will tend to this. This is how the flow looks. When it can be up and down, anything. I'm just showing some arrows in the random direction. It can be from down to top also. The flow is like this. They will get close to that lines, but they'll never touch the lines. Aisa. This is how the flow will look. The arrows can be down also. I'm just showing you any direction. It could have been anything. We need more information to find exactly which way it is flowing. Clear with this? So that is how the streamlines will look on this. This is also rectangular hyperbola. Right? Every time xy constant nahi hoga. You will learn max, don't worry. There's something called asymptotes. You will learn in that. So for this equation, x minus y and x plus y are the asymptotes, which are perpendicular to each other. That's why it's called a rectangular hyperbola. ऐसा कुछ था. Don't worry about it. Clear with this? So using the same logic, let me give you one. You try. Let's say velocity v bar is a plus bx I cap minus by j cap. So this is the velocity of a particle on a streamline. A and b are constants. Find the equation of streamline and approximately try to draw the path.
So can you go to the last slide for one second? Thank you.
So tan theta is Vy by Vx minus By by A plus Bx. So dy by y is minus B dx by A plus Bx. Integrate this. This will be ln y. This is minus B by 1 by B ln A plus Bx plus some constant. So this will be ln y by A ln y into A plus Bx is constant. So this turns out to be y is equal to C by A plus Bx. C is some constant. So for different values of C, you get different paths. So if you try to plot them, try like this. If I put y, let's say if I put x is equal to 0, what do I get? If I put x is equal to 0, y will be some constant. So it will start from some here. And as x tends to infinity, what will happen to y? 0. So the streamline will go like this. So this is for some constant C1. If you take another constant C2, because it depends on this constant now, so it will start here and this will again go like this. No one will touch each other. They'll actually keep going till like this, the gap. They'll just keep getting closer and closer. This is C3, they'll get closer and closer. If you take negative constants, this is how this flow look. So it will depend on that constant. So for different values of C, so this is variable, different values we can have. This is constant, but can have different values. This can have any value. If you take C0, you will get a line, center line, isn't it? So that is how the flow will look like. The streamlines are getting closer and closer and closer as they go towards plus infinity. So these are the values for C greater than 0. These are the values for when C is negative. Got this? Exam they'll ask you this. Which of the following is the streamline flow? Meaning the equation of the streamlines or the path of the streamlines. Clear na, Aditya? Aryan? Rehan?
Sir, and the values you'll get when they give you the limits, right? The constant ka value.
हाँ, कुछ तो देना पड़ेगा उनको data. Clear? Next one. Clear na, Yasha? Pastika, got this? Udayan, Ali? Perfect. Next thing, equation of continuity. So this is nothing but law of conservation of mass. They'll ask this kind of questions in CET. Yeah? Equation of continuity is based on what? Law of conservation of momentum, moment energy, angular momentum, mass. They do ask such dumb things. And people do leave those things also in come. So if this area is A1, liquid enters with V1. This area is A2, liquid comes out with V2. If you take a thin cross section here of dx1, thin cross section here of dx2, the mass entering should be equal to the mass leaving. Steady state. So that will be density A1 dx1 should be equal to rho 2 A2 dx2. So that will be the mass by time. Rho 1 is equal to rho 2, incompressible fluid. So you end up with A1 V1 is equal to A2 V2. So this A1 V1 is nothing but volume flow. Volume flow per second, that is how much liquid is flowing per second, is given by area into velocity. So this is the reason whenever you're playing with your water car tap, you must have noticed it. When you put your finger there blocking the water, the speed becomes more. The area becomes less, velocity becomes more. Because in that same space, the liquid has to flow faster. So if you try to write this vectorially, if this is your velocity vector, this is your area vector with theta, we can write volume per second is A into velocity in the direction of area, AB cos theta, can be written as A bar dot V bar. So we can also call this thing as Q, flow rate. We can use a symbol Q for flow rate. Meaning, let's say a river is flowing like this, and you want to find in this region how much water is flowing. You can take any random region you have taken like this, or think of like this. Rain is falling like this. You went outside and you kept a bucket like this, and you want to know how much water is getting collected in the bucket. So flow is going which way? This way, right? V, and the area of the bucket A is this way, na? So the amount of water getting collected in the bucket is AB cos theta. Make sense?
So is that the way they measure in? rainfall.
Yeah, rainfall they don't do itna fancy kuch nahi hai. They'll just put a bucket outside and they'll see in 1 hour how much gets filled. If it gets filled 1 centimeter, they'll say that today's rainfall is 1 centimeter. Ever observe? They measure rainfalls in centimeters and meters, mainly meters actually. So that's what they do. Itna kuch fancy nahi. They just put a bucket outside. So anytime you want to just do some nonsense, you can take a mug of water and put it there secretly. They'll measure more rainfall. So if that is a rain there and you want to see how much water is getting collected inside, that is how we measure. This is theta, this is area, and this is V. So rainfall collected per second is AV cos theta. Clear? Why you want to conserve angular momentum? Where is the torque zero? When you say angular momentum, you should talk about torque. So tell me about which axis torque is zero, then conserve angular momentum. But that is irrelevant actually right now here. Whenever you say angular momentum, first thing, you should talk about the axis. Define your axis. Right?
The horizontal axis below that pipe.
Horizontal axis below the pipe. And उसके बाद क्या करोगे?
Conserve between the stage where it is entering and where it is leaving.
Why you want to know? How can you conserve first of all? Do you mean to say there are no forces acting on this liquid and this liquid? Do you know what other forces are there? You don't have any idea about it, right? You don't know why it is going with V1. You don't know why it is coming out with V2. We just know if it goes with V1, if it comes with V2, this is the relation. We don't know why you got V1 in the first place. So, clear? Example. This thing, right? You can always use it even for multiple openings. So let's say liquid is entering with V1, area is A1, V2, area A2, V3, area A3. This is V4 and this is A4. What will be the relation between them? The liquid entering is A1, V1 plus A4, V4 should be equal to the liquid flowing A2, V2 plus A3, V3. So you can apply this even for multiple entrances and multiple exits. Clear? It is just not necessarily like it's a single opening and single this thing. Let's see a question.
A4 is a liquid under R.
A4? A4 is entering inside. So liquid is entering from 1 and 4 and leaving from 2 and 3. Clear? Then we have a building 20 meters high. And from here, you're sending a water jet with speed 10 meters per second at an angle 60 degrees. And the area of cross section is A. So as this water jet flies, something happens to the area. It's projected with P 10 meters per second. So when it hits the floor, this is how it looks. So this is the area where the water jet hits the floor. Basically, this area we are talking. So the question is, so basically this FBD we are drawing here. First thing, what happens to the area of the water jet? Options will be, it will always increase, it will always decrease, it will increase and decrease, it will decrease and increase. What happens to area of cross section of water jet? Second part, find maximum and minimum area of water jet till it hits the ground. Third, the area of, the area, find the area when it hits the ground. Find the area. Basically, this area I want you to find. I'll write this one. So basically, find this area. Find the area on the floor hit by the water jet. Question is clear? There, kinematics and this. Okay, right, Utsa. Get the remaining. So we have a water jet of area A. You're projecting it 60 degrees at 10 meters per second. What will happen to the area of cross section of the water jet? Increase, decrease, increase and decrease, decrease and increase. So 4 options. Right, Anusha? Second, what is the maximum area and what is the minimum area? Third, when it hits the ground, it will spread on the ground to a certain area. What is that area on the ground? Anyone not clear with the question? Ask me. Question is clear? Try. You got 2-3 minutes. Let's see. So first thing, yeah, as the velocity goes up, what happens? It increases and decreases. So at the highest point, the velocity is u cos theta, which is u by 2. So area will be two-way, isn't it? So first thing, the speed decreases till h max and then increases. Therefore, area increases, so the flow it becomes more thicker and decreases. That's your maximum area. And when do you get the minimum area? You get the minimum area at the bottom. So at this point here, the speed is v. How to find that speed v? Maximum area will come at h max. So max area at h max. We are using A1 V1 is A2 V2. So which is 2A. So minimum area will occur on the ground. How do you find that speed v? Conservation of energy. Half mu square. If you try to use, kinematics, you'll get it, but it'll be quite long. Half mv square. That will be m will cancel. U square is 10 square. 50 plus g is 10 into 20, 200. And this would be half into v square. That is v is equal to 10 root 5. So initially it is area. Velocity is 10 is equal to final area is a dash, and this is 10 root 5. Clear? How much is this? A by root 5. So this answer is a by root 5. But the third part, that is not the question. Third part, how does it look? See. If you look at this water jet, it is coming and hitting like this. This area you found A dash. I'm not asking you that area. So when this thing goes and hits the ground, it spreads, na? If you take this angle is alpha, this angle will be alpha. So this area will be A dash by cos alpha. That is the area it hits the ground. Remember this? The water jet hitting, that ellipse wala area hitting at an angle kiya tha humne equation pressure ka. Now what is that alpha? That alpha is not 60 degrees, gods. U cos theta is equal to V cos alpha. Bhul gaya kya? Kinematics. Horizontal velocity always remains same. So U cos theta is half and V will be 10 root 5 cos alpha. Actually, this is A dash by sin alpha. Cos alpha. Opposite, that's an opposite side actually. Sin alpha, isn't it? So from here we get cos alpha is 1 by 2 root 5. So from there we can find sin alpha. Root over 1 minus this, 1 minus 1 by 20. That's your answer. Clear what I did? What you found here, A by root 5, is this area when you're hitting the ground. This area you're talking. When you hit the ground, you get something else. You get A dash by sin alpha. Confused? Clear?
So I didn't understand how we're getting the slant area, like not the area.
Arey God, when you hit the jet aisa aega na. What you're finding is this area. When you say A1 V1, you're finding this area, isn't it?
Acha, okay.
जब angle पे hit करेगा तो ये you will hit the ground this area, right?
Yeah, but why is it giving us that area, not the niche wala area?
What you talking?
Matlab, why can't we apply equation of continuity directly for the niche wala area?
Okay, so how is the velocity this way
Yeah,
or
like
this way?
oh,
Velocity is which
अच्छा,
way?
ठीक है.
Velocity is this way ना God.
Yeah.
तो वो area लेंगे ना.
Got it.
Got it. You should take the velocity perpendicular to the area.
Right, got it.
All got this diagram? समझ में आ रहा है ना क्या कर रहे हैं हम exactly? It spreads over. It'll get an ellipse actually. There, kinematics, work power, energy, and equation of continuity. Clear? Let's see one more based on this. Something similar. Any doubts? Vidyut, clear na? Clear? Better now? Yeah. Just because you're not getting problem, don't harm yourself. Vidyut, whenever he doesn't get a problem, he cuts his finger. That is commitment. Mary accidentally poked his finger with his pen, it seems. होता है कभी कभी. So I used to do that. Whenever I never used to get a problem, I used to do 5 push-ups. Keeps you physically fit. I told you how I used to study inorganic chemistry with my friends. He'll ask me 3 questions every day. I'll ask 3 questions every day. For every question that you don't answer, you can punch me once. So we used to mix physical violence with subject. So that way, right, we used to learn faster. And we used to be strong also. Next one. This, it's a good question, but every time I have a problem drawing the diagram. So I'll try my best. Appreciate my artistic skills. So we have a semicircular plate. Maybe I should draw it sideways, I guess. Shit, I hate this. Let's see, I have one small diagram. Where are you, God? There's some stupid issue with this. Okay, I'll try. So we have 2 semicircular plates. I'll just start from the top view. So it is like this. So here liquid is entering. I'm not getting this. We'll do this later on. Next one. I gave up. Wait, one last try. I don't know why this is not loading. I think this is what is happening. Just give a sec, I got it. Seriously. Waste of time. So we have a semicircle. We have one more semicircular plate like this. Each में ना you have a gap like this. Thoda better, able to visualize. So it's like an opening. So if you see the top view, it's like this semicircle on top of it a semicircle. So this is R1. This is R2. So what is happening here? The liquid is flowing from here, the center. The liquid is flowing like this radially throughout the pipe. We can't ignore this. You're getting how is the flow? The thickness of this is T. The inner radius is R1 and R2. Rho is the density. And if you see the flow here, the flow is actually going like this. So basically, as it goes out, it spreads over. Diagram समझ में आया? ठीक है? This is the thing. So two semicircular plates. I'll try to get a diagram. Let's see what. Of inner radius R1 and outer radius R2. So liquid flows between the plates. The distance between them is T. Liquid enters with speed V naught. So here when it is entering, here the speed is V naught. From R1 and leaves from R2. Distance between the plates is T. First question. Find the speed of the fluid as function of time T, as function of distance X. Find speed of fluid as function of X. X is the distance from the center. So X ka value lies between R2 to R1. Are able to visualize how the liquid is going? It will spread out like a semicircular shape, na? Find momentum and kinetic energy of the liquid between the plates. Second is a pretty good one, right? Especially the momentum part. If I ask this, it will be a proper advanced question. Find momentum and kinetic energy of liquid between the plates. At any point of time, it's moving with some velocity. So you need to find the momentum and the kinetic energy. There is a stupid diagram. Why is this not getting updated? Kuch wise. Okay. Anyone didn't get the diagram, please ask me. I can't draw better than this. How do we get this 3D effect, right? How to do? Find the velocity as function of x. That's an easy one. The momentum is a tough one. Again, what is the formula? A1 V1 is equal to A2 V2. I didn't teach you anything else. Where A is the area in which the liquid is flowing through. V naught R by R1 plus X. Huh? See now. Again, if I'm just drawing the top view, so from the center at a distance x, if you take a semicircle, right? The area will look like what? The side view will look like this. How do I show this strip? Pray God. No one knows how to draw this. Okay. You'll get a strip like this thing, no? That semicircle thing. I'll give up drawing that. You'll get a semicircular wall. Stupid thing. I will be able to visualize, but I'm not able to put it on a paper. There, I'll just draw till here. And then suddenly it becomes vertical here. It looks so hopeless. Okay, so the thickness is how much? T, na? So the area will be how much? Circumference, which is pi into x into t. Agreed? Able to visualize, you'll get a semicircular wall, jaisa, whose circumference is pi x and the thickness height is t. There is this thing is not coming. Circular motion, there is a diagram, something like that. There, yes, I got the semicircle thing. ऐसा कुछ दिखेगा. Getting it? So this length here is pi x. This thickness is t. So the liquid will flow in this area, na? Better? Now you got the thing, how the view is. So A1 V1 is equal to A2 V2. So initially the area is pi into R1 into thickness t and velocity is V naught. After going a distance x, the area is pi x into thickness is same, and let's call it V subscript x, or let's call it V dash. So V dash will be V naught R1 by x. Easy, na? Itna hi karna tha. Okay. Take x from center, na? It will make life easy. Easy? Velocity part? How to find the momentum part? Take a break. Come back by 7:15. We'll continue there. Now, those who want to try, continue trying. You can try. If you don't want a break, continue the momentum and the energy part. But take a break. Come back by 7:15. We'll start in 6-7 minutes. Any doubt so far? Anything you're not clear? So you need to find the kinetic energy and the momentum of the liquid between the plates. Remember, liquid is not going in the same direction, it is going off in different directions. Sure. Comes on. Let's start off. So this is the diagram I was saying. The flow is coming out like this. Clear? Now, how do you find the energy here? Find the momentum and the kinetic energy. Momentum rho pi r2 square r1 square. Nay God. No, it's not that. Momentum is a vector quantity. Don't forget that. You can't just directly add it up. I cap j cap like integrate करना पड़ेगा. Try. I'll give you a minute. Think about it. How to find momentum. I'll give you a little idea. See. If you take the top view, from the center at an angle, let's say vertical से लेते हैं, because momentum is a vector quantity, so you can see by symmetry angle theta. So at a distance x, take a small dx and a small arc rd theta. You get a piece like this. This piece will be rd theta. And this piece has a velocity v dash. You know, how will the piece look like? You get a small cuboid where this is dx, this is t, and this is rd theta or xd theta in this case. समझ में आ रहा है? And this piece has a velocity v in this direction. So we find the momentum for this small piece and then we integrate. Abhi try karo. This is your hint. How to do from here. Because momentum is a vector quantity, you can't directly take m into v. And velocity same nahi hai na sabka. Everyone has a different velocity. And every strip will be different. So and from this you can see there is a symmetry. Did you observe? I can take a similar piece here. This also will be v dash. So only vertical momentum will be there. Na? Horizontal momentums will cancel off. So you just need to integrate the j cap component. V dash ka velocity is how much? V dash is v naught r1 by x, where x is the distance from the center. Did everyone got this thing, what I'm saying? Yeah, try. So you need to find the kinetic energy and the momentum of the liquid between the plates. Anyone not clear with what I showed you right now here on this page, please ask me. And I told you before, whenever you integrate vectors, you always have to integrate I cap, j caps. You can't directly add the vector. So mass of this piece will be density xd theta, thickness dx. So momentum of this small piece will be dm into v dash sine theta I cap plus cos theta j cap. then the momentum of the liquid will be rho T x dx sine theta d theta I cap plus cos theta d theta j cap. Double integration. This integration theta will go from minus 90 to plus 90. This integration will be x will go from r1 to r2. There are two variables here. X is changing, theta is also changing, isn't it? So you have to double integrate that. Meaning when you're integrating for the entire semicircle, and then you're integrating all semicircles. समझ में आया ना? Meaning of double integration. So when you go from minus 90 to plus 90, so here theta is 90 and theta is minus 90. So you are covering a semicircle. When you go from R1 to R2, you're covering all semicircles. Get this? This much you can handle now. Anyone confused with this equation? Ask. If you got this, it is done. Question is over. Abhi sirf max plus hai. Wait, there is one more I forgot. B dash नहीं लिखा मैंने. B dash में there is one more V naught R x1 ना. So V naught R1 by X, so this X will cancel off actually. Substitute this V dash here. Anika, clear na? Abhinav? Got this? Anusha, Aditya? Aryan, clear with this? Vartika, understood na? How did it choose the element momentum for that? So iska integration will be rho V naught R1 T. X ka limits will go from R2 to R1. And this integration will be sine theta d theta ka integration is minus cos theta. Minus pi by 2 to pi by 2 I cap. ये तो cancel हो जाएगा anyway. And this का will be sine theta to minus pi by 2 to pi by 2 j cap. So this will be rho V naught R1 T R2 minus R1. This will be 0 plus 2 j cap. As expected, it is only in the j direction. 2 rho V naught R1 T R2 minus R1 j cap. Please check. Clear? If you think about it, it is more about choosing an element and solving. That's what makes this problem good. And more of the visualization in the diagram is a messed up thing. Question अभी तक हुआ नहीं. Kinetic energy निकालना है. Kinetic energy is more easy. Why? You don't care about I cap, J cap, isn't it? Kinetic energy, you can take that entire strip. Because kinetic energy direction doesn't matter. Try. I'll give another minute for kinetic energy. Anyone confused with this thing, please ask. Especially I'm worried about these three equations. This, and this. Anything that you're not clear in those three, please ask. The mass ka part, mass into velocity, vector component, I cap, J cap I did, and then double integrating because there are two variables there. Your momentum is changing with X also and theta also. How to find the kinetic energy? Rho ln के terms में आएगा God. If you take a strip like this, so dm will be rho pi x thickness into dx. So you're taking a thin strip. Whose width is dx. Total angle is pi. So this is the mass of that semicircular strip. And don't forget, this entire strip is going with v dash. Speed is same at that distance. So kinetic energy will be integral of dm v dash square of rho pi t x dx. V dash square is v naught square r1 square by x square. Limits will go from r1 to r2. So rho pi t v naught square r1 square by 2 integral dx by x. Rho pi t v naught square r1 square by 2 ln r2 by r1. Check. Like I said, kinetic energy is the easy one. I cap, j cap, kuch headache nahi hai. Directly take half mv square and you're done. Have a look at this. There. Equation of continuity, normally questions are easy only, but you can ask such kind of things also. Like I said, this question is more of a headache because of that visualization only. Clear? Any doubts on this question? It's a good one. There's actually even a better question in this. This thing is based on Bernoulli's actually. Meaning later on we will see. Bernoulli, remember P plus half rho v square constant. The velocity is changing, pressure is changing now. That means on this semicircular plate, different points have different pressure. To find the net force acting on a circular plate, you have to find pressure at a point and integrate with area. You can ask like that also. Clear? Next one. Any doubts on this question? Rehan, Palak, clear with this? Vidyut, Aryan, Ali, Udayan? Great. Next thing, Bernoulli's equation. We are not going to do the proof. It's not that important. But maybe I'll just show you, I guess. Let's see. This is another form of law of conservation of energy. So first thing, it is valid only for streamline flow. This is based on law of conservation of energy. So what this thing says is, let's say area is A1, V1, P1, P2. Area is A2. So P2 is the pressure. Let's say this height is H2 and this height is H1. So here we know equation of continuity A1 V1 is equal to A2 V2. This comes from equation of continuity. So this is nothing but A1 dx1 is equal to A2 dx2. You can just divide dt, then you can remove that. So what we are doing here, we take a thin strip here, dx1, we take a thin strip here, dx2. So Bernoulli's equation is actually nothing but work per energy. So work done by pressure, that is external forces, is equal to change in kinetic energy plus change in potential energy. So here the pressure will be P1, A1, that is the force on the left hand side, into displacement dx1. On the right hand side, force is P2, A2 into dx2, that is the displacement. The change in kinetic energy will be half dm v2 square minus v1 square plus dm g h2 minus h1. So we can arrange this. So P1 A1 dx1, P2 A2 dx2, dm is nothing but rho. Again, you can choose any one, A1 dx1. Mass is same. B2 square minus V1 square plus dm is again rho A1 dx1. Or best thing, wait, I'll do one thing. I'll just multiply and divide by rho here. So P1 by rho will become rho A1 dx1. P2 by rho, this will become rho 2 A2 dx2. This is nothing but mass. dm will cancel off. You end up with simply P1 minus P2 is half rho V2 square minus V1 square plus rho G H2 minus H1. If you rearrange this, you end up with P1 plus half rho V1 square plus rho G H1 is P2 plus half rho V2 square plus rho G H2. Means at any point on the liquid, this quantity P plus half rho V square plus rho G H is constant. So if you look at these terms, this is nothing but actually work done by pressure is change in kinetic plus change in potential. It's nothing new. Have a look at this. Derivation is not important. It's only boards may they might ask you, but there you can't write like this. There you'll write more stories. Consider a liquid of section dx1 thickness. Area is A1. So sub story is important. Clear? Let me just write this properly. So P plus rho GH plus half rho V square is constant. P is the pressure at a point. H is the height of the point above the reference. V is the velocity at that point. So there's a name for this. This P is called actually pressure head. What it means is work done per unit volume. Remember, pressure into volume is energy. This is called potential energy head. That is nothing but potential energy per volume. This is called kinetic energy head. That's the terms they use in HSE also. So there's nothing but kinetic energy per unit volume. It is important because they'll ask you in units and dimensions. Find the kinetic energy head. And you should know it means kinetic energy per unit volume. This is the formula there. Remember, this is valid only for 2 points on a streamline. This is not valid between streamlines also. Means if you're having streamlines like this, So if this is 0.1, this is 0.2, this is 0.3, this is 0.4, and this is 0.5. You can apply between 3 and 4. You can't apply between 1 and 4 or anything. You're getting it? So this is valid between 3 and 4 because they're both are on the same streamline. But luckily what happens now? At any point we can say streamlines are looking symmetrical, and therefore we'll say 1 and 3 are identical, therefore 3 and 4 are also same. So we work out like that. But theoretically, if they ask you a question, Bernoulli's equation is valid between 2 points on a liquid. No, wrong. It is between 2 points on a streamline. Getting the difference? You can't apply Bernoulli between any 2 points in a liquid. They're on the same streamline. Now this, we have a variation of this Bernoulli's theorem. Modified Bernoulli for gases. So what is this modified Bernoulli's thing? Especially we use this for gases, because whenever gases expand or compress, the temperature changes. So this is how the formula becomes: pressure plus rho GH plus half rho V square plus du by dV is constant. Where du by dV is the internal energy per unit volume. Can you see all the terms on the left hand side are energy per volume? So this thing, right, is uses when gases flow, temperature changes. So that means the energy is also losing, na? Heat is also getting converted. When gases flow, temperature changes. Generally in a liquid, we assume temperature is constant, so that's why we don't include that. When gases flow, temperature can vary. Therefore, we include internal energy ka term. Therefore, change in internal energy is included. Suppose if the temperature is not changing, then there is no need to use that. But if temperature is changing, we use this internal energy per unit volume. We will do a question on this later on. So don't think in terms of Bernoulli, think in terms of energy conservation, isn't it? End of the day, it is an energy conservation. So whatever work you're doing, it is used to change kinetic energy, used to change potential energy, it is used to change temperature also. Now, if you think that way, it doesn't look like something weird. Clear? Got this? That is one. So let me ask you a question. This thing I can actually ask in flux here only. Top view. Let's say we have a pipe like this. So this area of cross section is A. So till here also it is A. Then the pipe becomes actually A by 2. This becomes A by 2. So, and you're sending liquid here with a speed V. This is the top view. On both the sides, you have atmosphere only, P0, P0 and everything. So the question is, now if the liquid is flowing through this, find the tendency of this Z shape thing, in which direction will this move? Because of the liquid is flowing, this will try to move and this will try to rotate. So options will be like this: in which direction will it move and will it rotate? So a liquid, this is placed on a smooth ground, flows in a Z-shaped pipe on a smooth ground as shown. Find the direction in which the pipe moves and rotates. Options will be: it will go up, it will rotate clockwise; it will go left, it will rotate anti-clockwise; it will go right, it will rotate clockwise; it will go northeast, southeast. Is options hoga. That is translation. Rotation will be clockwise, anti-clockwise. Pipe moves and rotates. This is actually based on equation of continuity only. It's not Bernoulli. Forgot to give this. How is the question clear? So liquid is entering with V. It won't come out with V. So this creates a problem. There's a difference in force. So this will try to move and will try to rotate. Which direction will this move and which direction will it rotate? Anti-clockwise and right, anti-clockwise and towards west. I know you're pretty close, Aryan, but you guys are goofing up. यहाँ पे भी कुछ effect पड़ेगा. Take that also into account. Now you'll see more clearly. Try again another 30-40 seconds. Then I'll show you. Anyone confused the diagram, please ask. See what will happen. Remember the water jet formula? So if a water is coming out with V, it generates a force of rho A V square. So there are two things here. Listen, when this water is coming and hitting here, it will generate a force of rho A V square. And when the water is going this way, it will push the container back with rho A V square. You're getting it? If you're going out, you'll push it back. If you're hitting the wall, you'll push the wall forward. Now, once you enter here, the speed is still V here. The speed here becomes how much? Double, na? So here the force will be rho A by 2V whole square. The force has become 2 rho A V square. So when you make the hole smaller, you get actually more force. And this will be 2 rho A V square. So what is the net force direction? So this guy is pushing this way and this guy is pushing this way. Make sense? So this will be 2 root 2 rho A V square. And this will be root 2 rho A V square. So the net force in which direction? Southwest. And which way it is rotating? This way, no? Clockwise. South, sir. Clockwise ना रे God. इस तरफ rotate करेगी, इस तरफ rotate करे.
correct.
You did everything and you messed up the last thing.
Ah.
Clear, everyone? Any doubts on this? So basically, na, you have to consider this thing also. So there'll be a vertical component of force also. If the pipe had been like this, everything is area, and suddenly then it becomes A by 2 here, then the force only will left and right. Aisha, got it? Arjun, got your mistake, na? Didn't take the vertical thing. Clear, na, Anika? Great. Next one. So extension of this. So what if the pipe is bent at an angle? So force on a bent pipe. In a horizontal plane. So let's say this is theta here. P1 pressure. Let's say V1. Area is A1. Pressure is P2. This is V2 and area is A2. So on this thing, the forces will be pressure into area, P1 into A1, and also the water jet ka force, rho A1 V1 square. This will be rho A2 V2 square, the water jet ka force, plus the pressure P2 A2. And we also know A1 V1 is equal to A2 V2. Equation of continuity. That is one. And the pressure difference, right? We can write P1 plus half rho V1 square, Bernoulli's equation. P2 plus half rho V2 square. This comes from Bernoulli's equation. Same height, so H1, H2 are equal. So exam will not give you all the values. They'll just give you P1 and A1 and V1, and they'll ask you to find the force. So the resultant will be P1 A1 plus rho A1 V1 square, and this force will be like this. P2 A2 plus rho A2 V2 square. This angle is theta, so this angle is 180 minus theta. Then you can take I cap, J cap and find the resultant. So the net force will be something like this. Previous problem, na, I gave you that's why pressure P not outside. So you didn't care about pressure. But if you take up liquid flowing in a pipe, pressure won't be equal. You have to consider P1, P2s also. So that is one additional thing. So if you take a small cross section of the pipe, the pressures won't be the same inside. So this is a better version of what we did. Next thing. Now in fluid dynamics, right, there are four things actually. One is the velocity of efflux, Magnus effect, and then we have aeroplane wing basically, Venturi meter and siphon. The main important thing is the velocity of efflux. We'll finish off the derivation today. We'll do some good problems on that in the next class. So velocity of efflux. So this is nothing but consider a container with a hole of area small a at a depth h from the surface. So the speed with which the liquid comes out of the hole is called velocity of a flux. So if you take a container and if you take a small hole here, this area of the container is A. Let's say this thing is filled with liquid. And this is height h. So this liquid comes out here. This is called velocity of a flux. So let's see, we want to derive that thing now. So take a small hole here. So if you look at the liquid flow, this is how the streamlines are. So the whole liquid is going out like this. Let's call this thing V2 and let the speed be V1. And let the height of the liquid be h. So this point on the surface is 1 and the 2 is outside. So point 1 is on the surface. Point 2 is just outside the hole. So first thing, using equation of continuity, A1 V1, that will be A into V1 is equal to A into V2. Second thing, Bernoulli's equation, P1 plus rho G H1 plus half rho V1 square is P2 plus rho G H2 plus half rho V2 square. Now remember, P1 and P2 should be equal to P0 because both are exposed to atmosphere. Point 2 is outside the hole, 1 is on the surface. So this will be P0. Height will be rho Gh. Velocity is half rho V1 square, but V1 is nothing but A V2 by capital A ka whole square. This is P0, whole is the zero height and half rho V2 square. P2 will cancel. You end up with V2 is equal to root 2 GH by root over 1 minus A square by A square. This is a result which you need to mug up. And remember, H is the height of the liquid above the hole. H is not height of the container. Now, if the hole is very small, then the term A by A will tend to 0. Then the velocity will become approximately root 2gh as if it is freely falling. So use the formula root 2gh only when they mention if the hole is small. If they don't mention and if they're giving you the areas, you have to use that root 2gh 1 minus A square by A square. 2006, this question came in the exam. Straightforward question. They gave the area of the container to the base is 50. They said A by small a is 50. I thought अरे बहुत छोटा area है, so I use root 2 GH. When I check the options, I got 49.5 something. Options are 49.5, 49, 50, 50.5. They're pretty close. I said like, yeah, कुछ तो suspicious. I said like, yeah, just to be sure, I use this formula. I got exact 50. And that's the answer. I came outside and all my friends are jumping. Oh, it's an easy question. Everyone messed up. So yeah. Have a look at this. So just one Bernoulli's equation and equation of continuity, you get the velocity of a flux. Clear with this? All got this? Now I have a small query here. Suppose if I take a point here, 3, just inside the hole. Can I apply Bernoulli between 1 and 3? Can I solve the problem taking 1 and 3 instead of 1 and 2? क्या problem है? And so I took same streamline, na? It's the same streamline. I am taking point 1, 3, and 2 all on the same streamline. 2 is just outside, 3 is just inside. It is streamline flow. उसका tension नहीं है. Just inside ना रे. So area is almost A only. What you're saying is true. If I take 3 somewhere here, then it's a problem. Just inside, just outside. So it is almost the same. What is the issue? Can I use yes or no? Or कुछ नहीं है. Pressure, what is the problem? You cannot write P3 is equal to P naught plus rho GH. Why? Liquid is not at rest. This is for static equation, na? Here the liquid is moving, isn't it? Liquid is accelerating. Since V1 changes, V1 is changing with time. Therefore, the liquid is accelerating. So you can't write. So basically, problem kya na? You can apply, but I don't know P3 ka value. Are you getting the point? But there's something interesting happens. If the hole is small, then A V1 is equal to A V2. Then V1 will be A V2 by A. This is tends to 0. Therefore, we can say acceleration of liquid tends to 0. Therefore, we can say P3 is approximately P naught plus rho GH. For small holes, we can use this. If the hole is big, this is messed up. Clear? Now, this gives an interesting result. But I hope everyone understood why we can't take 3. It is not wrong. You don't know P3 ka value. Clear? So this is the variations of this. It's a very useful result to remember. So if you have a container, so the velocity of efflux V is given by root over 2 times delta P by rho. This is velocity of efflux, where delta P is difference in pressure just before and just after the hole. Rho is the density of the liquid which is coming out. This is the result, valid only for small holes. Getting it? Now see, you get pretty nice cases. So if you take our problem here, just now the one we derived, because see the Bernoulli's theorem, end of the day, it is interested in the pressure, right? So if you take height h, density rho, so here and here, what is the pressure difference? P naught plus rho gh. It's a small hole, so you can do this. Minus P naught. So pressure is rho gh. So velocity will be root over 2 times rho gh by rho root 2 gh. Got this? Suppose if I give you a case like this, then what will you do? So this is one case. Suppose if I take a container, let's say there's a liquid here, rho 1, let's say there's a liquid here, rho 2, and let's say there is a liquid here, rho 3, whose height is h3, whose height is h2, whose height is h1, and let's say you made a small hole here. Now what is the velocity of flux? Remember, if you take the pressure difference between this point here and this point here, so P1 minus P2 kitna hoga? P1 is P naught plus rho 1 G H1 plus rho 2 G H2 plus rho 3 G H3 minus P naught. Again, a delta P. So what is the formula? Root over 2 times delta P by rho. Which rho will you take? The liquid which is coming out. So 2 delta P by rho 1. You're getting this? Because Bernoulli, you're applying for a given liquid, isn't it? Suppose if they ask you a question like this, they will say the container is sealed. There's a liquid density rho, height h, and this container inside the pressure of the gas is 3p naught. Abhi kya hoga velocity of efflux? You're getting the same cases, different variations. What is delta P here? Pressure inside and outside. So pressure just inside the hole and outside. This will be 3p naught plus rho gh minus p naught. 2p naught plus rho gh. Make sense? Put it in the formula, you'll get the answer. Suppose if I ask you this question, remember this cylinder rotating with omega, liquid here rho, length L, and let's say someone made a small hole here and it is coming with V. यहाँ पे क्या लेंगे? Remember the formula for a cylinder rotating pressure? So this is 1, this is 2. Let's check this is P naught here. So P1 will be P axis, which is P naught plus rho omega square L square by 2. P2 will be P naught. So यहाँ से you'll get delta P. You're getting all these cases? You can just keep playing around. You just need to find the pressure somehow and put it there. Clear, na, Vidyut? Vartika? Palaksh? Anushka? Anusha? Clear with this? One more case. Suppose you have a container, and this time you have a piston, and on top of it you kept a block mass in. Filled with liquid, height h and density rho. And let's say you made a small hole here. Abhi kya hoga velocity of flux? So basically from fluid statics, we need to just get the pressure somehow and put it in that formula and you'll get the answers. So here what is the pressure? P naught, because atmosphere bhi hai, plus block ka pressure mg by area, plus rho gh. Agreed? Outside the pressure is P naught. So delta P will be mg by A plus rho gh. Clear? These are some of the cases I can think of. Matlab, liquid on liquid, liquid with a higher pressure on the air, rotating cylinder, mass on the piston. So you bring any situation. Using statics, you find the pressure here and finish it off. But remember, this is valid only for the small hole. Why? When the hole is small, you can assume the pressure is almost P0 plus rho g. That thing is valid. Because if the hole is big, the velocity will be big and it will accelerate. You can't use your fluid statics ka equations. So quite a useful formula. Saves you a lot of time. Clear with this? 2 delta P by rho. Rho is the liquid which is coming out. Please check it out. Got this? So that's the last one for that day. So next class when we meet, we will do more deadly ones. This is nothing. I mean, these are good ones, but we have some good ones also. But do have a look at this. It's quite an important thing. Definitely mug up the formula because especially mains and bits, they ask questions like this. I remember there was a question like this in bits, I guess. And there was a question like this in mains. Pressure is 3P0 or 2P0. Most people didn't understand what to do because सबको एक ही formula याद था, root 2GH, root 2GH. Everyone mugged up this formula and went and no one had a clue what to do. But this is even a much better version of that same formula. Clear? You can use it in multiple scenarios. Okay, with that we'll wrap up for that day. So on Friday when we catch up, we'll finish another chapter and mostly we might even start off with viscosity introduction. So do make sure to give the paper. The thermodynamics paper is online. So okay, with that we'll wrap up for that day. So any doubts, anything, please stay back or else you're free to leave. So take care, stay safe, see you on Friday.